Welcome to homework.
In this problem, we are asked to write a program to solve the general case of problem 31 for any hydrocarbon fuel, CXHY, where H and Y are input parameters, and we wish to calculate the percentage of theoretical error for any given percentage of combustion products. So again, since I'm can't really write a program for you, I solved the problem in the general case and made some plots to show you what you need to program, and then the results that you should get. So again, we are told to assume a general hydrocarbon. I also used a variable n here um, to denote whether we have nitrogen or not. Um, if this is air, then we have this is 3.776. If it's just pure oxygen, then this is 0. So that allows us to look at two cases if we have air or pure oxygen. Doing stoichiometric balances, we just get these equations here. Notice that we have um, a, um, a stoichiometric ratio for a constant for oxygen as a reactant and as for a product. Now, what we can do then is, again, if we solve all these equations, we can get the mole percentage of dry CO2. So if we look at the total for all the dry components, again, we just take all the gases, because that's what we've measured on the dry basis. And then, so that winds up giving us this, where again we have the um, stoichiometric constant for the O2 and the products in here. Now, let's see here. We can then take take the ratio here, where we have the constant stoichiometric constant for CO2, which oh yeah, right here. And again, we can let's see here. We can take we know this is let's see here. We can well, yeah, we can then, so we have this. We can solve for all these things. Well, here we have um, VO2 of the reactants. So again, we can find this ratio here. We have this. We have this. We can find the stoichiometric constant for the oxygen in terms of, these are all going to be in terms of the stoichiometric constant for the fuel. So let's see here. We then get this ratio, and that ratio is a function of the hydrocarbon, and then simply the dry mole percentage of CO2, and then also the if we have that, whether we have oxygen or air or pure oxygen. So this ratio is all we really need to find is this value here. We don't need anything else to get our what we were looking for, because we know the stoichiometric ratio is this for a general hydrocarbon. And so if we want the percent or the theoretical error, we can divide this by this, and we get this expression here. So again, I define this x hat as to be the ratio of the x over y. And so you can see that for paraffins, that is n over 2n plus 2, where n is as an integer. For olefins, it's just 1/2, so it's constant. So for all olefins, this curve will be the same. And then for alkyl we have this. We have x hat is 6n all over 6 plus 2n. So let's see here. Notice that as n gets larger, these two things approach this. This approaches this as n gets large, and this approaches that as n gets large. So this is kind of a limiting case for both. Notice, however, that this approaches this as n gets large from below, and this approaches from above. So the smallest, the largest value we're going to have here is when n is 0 here, and that is the case when let's see here, when let's see, when this is just 1, and then when this is 1, that's when we have methane. Then this value is a quarter. I guess theoretically we could have n as 0, and that would mean that x hat is 0, and then we just have pure hydrogen. I guess I don't think I plotted that case. If this n is 0 here, then this is benzene. So we can make some plots. I made some 3D plots here of for air and pure O2. This is the percent theoretical air. This is the mole basis of dry CO2 on the products, and this is x hat. And I plotted it from 1/4 to 1. And then I chopped off this graph that is below 100%. So anything in this region here, we don't have, we weren't going to have complete combustion because we won't have enough oxygen. So we can see here that for, let's say for methane, we should have at least a measurement of our dry CO2 for complete combustion of this value here. I don't know if it's about 12%. And then as you can see that as the values increase for what we measure here, the percent theoretical error increases because obviously we get more CO2. Oh, sorry, as CO2 decreases, yeah, this is a decrease here. That means we just have a smaller percentage of CO2 because we're going to have more oxygen and nitrogen in this case in the mix. So this percentage is going to go down as our theoretical air goes up, and I went down to 0. So I think I've said before that this should be at least this. It should be at most that. It should be at most about 12%. If we have anything more, then we have theoretical error that would be less than 0, then our stoichiometric reaction would not be correct, our equation. And so we can see here that, again, as this goes down, we get greater and greater. This goes up to 300% theoretical error. As for benzene out here, again, we get a value here of a little over 15%. So again, this kind of curve as that ratio changes, the minimum or the maximum amount of CO2 in the dry products increases. Now, if we do it for pure oxygen, then we can see that we are always above 100% or at or above 100%, even if we measure 100% CO2, because we should, in 100%, we should just have H2O and CO2, and if we measure it on a dry basis, then we have 100% CO2. So that would be right here, and that means we have a just 100% theoretical oxygen. And as we decrease, as this thing decreases, that means our percent theoretical air increases. And so, again, we can see here as we go from different hydrocarbons, it doesn't change a whole lot. You can see that eventually, it does start to kind of increase as the ratio of carbons to hydrogens gets closer to 1 out here in this region here. But again, it's very flat here. So in regions where we have very close, less than greater than 50% dry CO2, then where basically there's not much change at all for as we change the hydrocarbon. Now we can make some plots for paraffins. So for paraffins, again, as n gets large, this approaches the olefins. So we can start with n equals 1 here, and we get this curve. And then as we go all the way up to n equals 16, you can see that they start to bunch up and approach, an asymptote here. And again, this point here is about 15%. Here it looks like we're at about 11.5%. So we shouldn't have anything above these if we're going to have at least 100% theoretical error. For oxygen, for pure oxygen, we have these curves. Notice again, we go all the way out here to 1. So that would be, these all converge to 1 at 100% at when we have 100% dry CO2. And you can see that down here in this region below or above about 60% or 50%, they all basically fall on this very similar line. And in fact, they're pretty close in general. And they start to approach this asymptote very quickly. Even for n equals 2, we're very close, and 3 and 4, and they just start to overlap. Now, if we look at, and again, this asymptote here is the olefins. Now, if we look at the alkyl-benzenes, they are basically all very much overlap one another. I only went to NS4 because that's what they only went to the book. So here we should have less than 17.5% dry CO2 in the mix for more than 100% theoretical error. And there's not much else to say. Again, they fell very much on the same curve, no matter what N is. And then again, for the oxygen, we have for pure oxygen burning, again, we go out to 100% here. And again, they all fall almost all on the same curve. So that's what kind of some of the results you should get. So if you write code, write those equations up in code and make some plots.